Moivre's theorem gives us a really nice way of proving some trig identity questions. So that's what we're going to look at today. Complex numbers and the trig identities. Start off with an example. Now, of course, we know these already, cos 2 theta and sin 2 theta. Let's pretend we don't. So we want to work out what they are in terms of cos theta and sin theta. We're using de Moivre's theorem. We know that cos theta plus I sin theta squared would be the same as cos 2 theta plus I sin 2 theta. If I expand the right hand side out, then we get cos squared, twice the product, so 2i sin theta cos theta, and minus sin squared. But the real part must equal the real part, and the imaginary part must equal the imaginary part. So therefore, cos 2 theta must be the real part, cos squared minus sin squared, and sin 2 theta must be the imaginary part, 2 sin theta cos theta. So quite a neat little way of proving those formulas, and quite a bit quicker than actually expanding out the sin theta plus theta and doing all that. But then that idea can be transferred to any power you like. So if I now wanted to find sin 3 theta, cos 3 theta, and what the heck, let's do tan 3 theta as well, I can do the same thing but with the cubic expansion. So there's a power of 3, so that'll be cos 3 theta plus I sin 3 theta. And that will go cos cubed, 3i sin theta cos squared, but then it would go 3i squared, well I squared is negative 1, so we've got negative 3 sin squared cos theta, and then the last one would be I cubed sin cubed, but I cubed would be negative I. The imaginary part equals the imaginary part, so there's 3 sin theta cos squared theta minus sin cubed, and if I want to put that just in terms of sin theta, then I substitute in for the cos squared 1 minus sin squared, tidy that up. Of course, there's no reason why I have to do that, because the question did say in terms of sin theta, cos theta and tan theta. So the very first line is in terms of sin theta and cos theta. So it's probably good enough for an answer. Mind you, the last line's a bit neater when it's all sin thetas. And then looking at the real part, cos 3 theta, again, that'll probably be good enough for an answer. But let's put it all in terms of cos theta, and sin squared is 1 minus cos squared, and we get our relationship for cos 3 theta. Now to get tan 3 theta, remember tan is sine on cos. So the relationships that I've just worked out, I'll substitute in. But you'll notice I've gone back to the very first line, what I've substituted in. So for sine, I've subbed in the 3 sin theta cos squared minus sin cubed, and on the bottom, the cos 3 theta, I've gone with the cos cubed minus 3 sin squared cos. Now the reason I've done that, I want to turn these into tan thetas. Now tan is sine over cos. So how to do it is we will divide everything by cos to the highest power. Remember, we're trying to get cos on the bottom of each term. So if I divide by the highest power, then every term will have cos on the bottom or no cos at all. So cos to the highest power, which is cos cubed. So the top becomes 3 sin theta on cos theta, sine on cos is tan, minus sin cubed on cos cubed, tan cubed, over cos cubed on cos cubed, well that's just 1, minus 3 sin squared on cos squared, tan squared. So now I can write it all in terms of tan. Now, we could keep going and do power of 4 and 5, but the idea is basically the same. Okay, another type of question. We're going to show that this is one of the solutions to 8x cubed minus 6x plus 1 equals 0. Now, if we go back to what we just proved, cos 3 theta is 4 cos cubed minus 3 cos. So just look at that pattern. 4 times something cubed minus 3 times something to the power of 1. Alright, let's go to our question. Well, I've got 8 times something cubed minus 6 times something. So that's why I've factorised the 2, but I've only factorised it out of the 2 terms. So inside the parentheses now I have 4x cubed minus 3x. That was that pattern of that cos relationship we just proved. So if I replace x with cos theta, then it becomes, inside the parentheses, 4 cos cubed minus 3 cos. But, remember we just proved that was cos 3 theta. It now gives me a nice little equation to solve. Just cos 3 theta is a half. A half's one of our exact values. So cos of what is a half? Oh geez, which way around does it go? Cos is 60 degrees, isn't it? So in radians that would be pi on 3. But it's a cubic that I'm solving. So I need 3 solutions. You want the same number of solutions as the power. As long as they're 3 consecutive solutions, we're fine. I always start with the first one, the obvious one, and then just keep going around the circle until I've got the right number. It doesn't have to be that. As I say, as long as you've got 3 consecutive solutions, this will work. So I've got pi on 3. The next one will be 5 pi on 3. The answer in the, well, that'd be the 4th quadrant. Then we're going around the circle again, so I add 2 pi to the pi on 3, 7 pi on 3. Now that gives me solutions for theta. Remember, we're solving for x. But back here, we said let x equal cos theta. So therefore x is cos pi on 9. That's the one they wanted me to show. Cos 5 pi on 9. Cos 7 pi on 9. So yes, cos pi on 9 did turn out to be one of those solutions. It wants me to work out what is cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. Okay, let's go back to what we just solved. We now know x are solutions. So cos pi on 9, cos 5 pi on 9, sin 7 pi on 9 are the 3 solutions, or the 3 roots of this equation. Let's go forward. We're trying to go cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. Product of 3 things, well, so product of the roots for our equation is 1 on 8. So cos pi on 9 times cos 5 pi on 9 times cos 7 pi on 9, not quite the same. I've got a 7 pi on 9, they've got a 2 pi on 9. Now we start playing with which quadrant is it in, odd even functions, all these sorts of ideas to try and get the one we want. So I want to turn this 7 pi on 9 into 2 pi on 9. Well, 7 pi on 9 is in the 2nd quadrant. So it would be the same as the negative, the cosine of the acute angle. The acute angle would be 2 pi on 9. So therefore I can substitute in for the 7 pi on 9 negative cos 2 pi on 9, and therefore my product is negative 1/8 as my answer. This relationship, z to the power of n plus 1 on z to the power of n, and the minus 1 as well. It's a good relationship to remember. If they don't ask you to prove it, it's certainly okay to quote it and use it. So let's actually work them out so we know how to prove it if we have to. Okay, z to the power of n, we know, de Moivre's theorem, cos n theta plus I sin n theta. 1 on z to the power of n is z to the power of negative n. So that'll be cos of negative n theta plus I sin negative n theta. Now I'm going to play with odd and even functions. Cosine is an even function, so cos of negative n theta will be the same as cos n theta. Sine is an odd function, so sine of negative n theta will be the negative of sine n theta. We want to find, first of all, when we add them together. Well, when we add them together, then the imaginary parts cancel and I get 2 cos n theta. So there's my result for z to the power of n plus 1 on z to the power of n. And for minus, well, now let's subtract instead of add, and we get 2I sin n theta. So as I say, perfectly fine to quote those, unless of course they've asked you to prove them. But as you see, the proof's fairly quick. Just playing around with odd and even functions and you've got it. So we can use this idea for, well, several types of questions. Here's an example of one. I'm now going to write an expression for cos cubed in terms of cos and multiples of theta. Okay. I want cos cubed. So I'm going to write 2 cos theta all cubed. But on the right hand side, remember, 2 cos theta will be the same as z plus 1 on z. N in this case is 1. So 8 cos cubed will be z cubed plus 3z plus 3 on z plus 1 on z cubed. Now, the beautiful thing with binomials is you get that symmetry with the coefficients. If you group them together, and you get that pattern again. So there we go. Z cubed plus 1 on z cubed plus 3 lots of z plus 1 on z. And then we use the idea again. Well, z cubed, now n is 3. So that will be 2 cos 3 theta. 3 lots of z, well that's to the power of 1, so n is 1. So 3 lots of 2 cos theta, 3 2's are 6. So I now have, or no, divide by 8. So almost there. Divide both sides by 8, and I now have cos cubed in terms of cos multiples of theta. So it's playing with the z to the power of n plus 1 on z to the power of n idea. Alright, 7b.